Look at your hand. Go ahead, hold it up. Look at it. The skin, the knuckles, the small architecture of bone and tendon underneath. You've had this hand your entire life. You know what it's made of? Cells, molecules, atoms, protons, and electrons and neutrons arranged by evolution into something capable of holding a pen, turning a page, touching the face of someone you love. You learned this in school. You are confident about this. You are, in fact, absolutely certain that when you look at your hand, you are looking at matter. You are wrong. Not completely wrong. I'm not going to tell you your hand doesn't exist. It exists. The atoms are real. The electrons are real. The chemical bonds are real. But here is what nobody told you in school, and what most people still cannot bring themselves to fully accept even after they've heard it a dozen times. The atoms in your hand, the atoms in this building, the atoms in every star you've ever seen in the night sky, the atoms in every galaxy we've ever photographed with, every telescope we've ever built, all of it, every particle of ordinary matter in the entire observable universe adds up to less than 5% of what's actually out there. 5%. The universe is not made of what you think it's made of. The universe is not primarily made of atoms. It is not primarily made of anything we have ever directly detected in a laboratory, anything we have ever seen with our eyes or our instruments, anything that interacts with light in any way whatsoever. 80% of all the matter in the universe, 80% of the gravitational scaffolding that holds galaxies together and determines the large-scale structure of everything is something we cannot see, cannot touch, cannot capture, cannot identify, and have never once in the entire history of science detected directly. We know it's there because of what it does. We have never seen the thing itself. We call it dark matter, which is a deeply unsatisfying name because it implies we understand something about it we don't. We know it's dark in the sense that it doesn't emit or absorb electromagnetic radiation. We know it's matter in the sense that it has mass and exerts gravitational force. Beyond that, we are, to be brutally honest, in the dark. The irony is almost too neat. I've been thinking about this problem for most of my professional life, and the longer I think about it, the more I'm convinced that dark matter is not just a puzzle about what the universe is made of. It is a puzzle about the nature of our own ignorance, about the limits of human perception, and about how spectacularly wrong our intuitions can be when we assume that the world we experience is the world that actually exists. That assumption, the assumption that seeing is knowing, that the visible universe is the real universe, is the assumption I want to demolish tonight, carefully, brick by brick, because the demolition is worth more than the building that comes down. Let me start at the beginning. Not the philosophical beginning, I'll get there, but the historical beginning, because this story has a human arc to it that I think is worth understanding before we get into the physics. The year is 1933. A Swiss-American astronomer named Fritz Zwicky is doing what astronomers do, staring at clusters of galaxies. In this case, the Coma cluster, a vast congregation of roughly 1,000 galaxies, about 320 million light years away from where you're sitting right now. Zwicky is measuring the velocities of individual galaxies within the cluster. This is not technically simple. He's using the Doppler effect, the shift in the frequency of light caused by motion, to determine how fast each galaxy is moving relative to the cluster's center. It's painstaking, meticulous work, and when he finishes and looks at the numbers, something is wrong. Not slightly wrong, catastrophically wrong. The galaxies are moving too fast, by a factor of several hundred. If you take the total luminous mass of the Coma cluster, all the stars, all the gas, everything you can see, and calculate how much gravity that mass produces, it is nowhere near enough to keep those galaxies from flying apart. At the velocities Zwicky is measuring, the cluster should not exist. It should have dispersed billions of years ago. The galaxies should have scattered into intergalactic space like shrapnel from an explosion. But there they are, bound, clustered, orbiting a common center. Something is holding them together, and that something is not visible. Zwicky calls it dunkel materia, dark matter. He proposes that the cluster must contain vastly more mass than the luminous matter can account for. The scientific community, with The characteristic open-mindedness that has always characterized scientific communities largely ignores him for 40 years. Now, here is where it gets strange. The vindication doesn't come from the study of galaxy clusters. It comes from individual galaxies. And it comes from a woman whose story deserves a great deal more than I can give it here, but I'll give her what I can. Vera Rubin. She was working at the Carnegie Institution in Washington in the 1960s and 70s, collaborating with the instrument specialist Kent Ford, and she was measuring something called rotation curves, essentially, how fast stars orbit around the center of spiral galaxies at different distances from that center. This is a measurement with a clear expected outcome. We know how gravity works. We've known since Newton. The prediction is unambiguous. Stars near the center of a galaxy, where most of the mass is concentrated, should orbit fast. Stars far out in the disk, far from the concentrated mass, should orbit slow. This is what happens in our solar system. Mercury screams around the sun at nearly 50 kilometers per second. Neptune lumbers at just over 5. The further you are from the mass, the slower you go. This is basic orbital mechanics. It is not controversial. It is not subtle. Rubin and Ford look at galaxy after galaxy, dozens of them over years of work. They measure the rotation speeds of stars at different radii from the galactic center, and what they find consistently, systematically, in galaxy after galaxy, is that the rotation curves are flat, not falling off the way they should, flat. Stars far out in the disk of a galaxy are moving just as fast as stars much closer to the center. In some cases, the stars at the edge are moving faster than orbital mechanics, as we understood it, said they had any right to be. This means one of two things. Either our understanding of gravity is wrong, or there is enormous amounts of invisible mass distributed throughout these galaxies, not concentrated at the center the way the luminous matter is, but spread out in a vast, invisible halo, spherical, extending far beyond the visible disk of the galaxy. If you put that mass there, if you add an invisible sphere of matter surrounding the visible galaxy, the rotation curves come out flat. The math works. The predictions match the observations. Now, I want you to hold both options in your mind for a moment, because this is where a lot of people make a mistake. They hear our understanding of gravity might be wrong, and they think that sounds more radical, more interesting, more scientifically brave than just invoking invisible matter that nobody has ever seen. And so there has been a persistent, serious, intellectually honest school of thought, modified Newtonian dynamics, or MOND, developed by Mordechai Milgrom in the 1980s, that attempts to explain the rotation curve data by modifying the law of gravity at very low accelerations rather than invoking dark matter. I want to be fair to this idea because it is not crazy. It correctly predicts the rotation curves of a remarkable number of individual galaxies. It is doing real science, but it has a problem, and the problem is devastating. It cannot explain everything else. Specifically, it cannot explain the bullet cluster. The bullet cluster is two galaxy clusters that collided and passed through each other about 150 million years ago. This is one of the most violent events in the observable universe. Two enormous concentrations of galaxies, each containing trillions of stars and vast clouds of hot gas, slamming into each other at millions of kilometers per hour. When this happens, the hot gas, which makes up most of the ordinary matter in a galaxy cluster, gets slowed by electromagnetic friction and lags behind. The galaxies themselves, being mostly empty space, pass through each other more or less freely. So after the collision, you have a situation where the hot gas, the ordinary matter, is in the middle. You can see it glowing in X-rays, and the galaxies are out on the sides. Now, if you map the gravitational mass of the system using gravitational lensing, using the bending of background light to find where the mass actually is, the mass is not where the gas is. The mass is where the galaxies are. The mass has separated from the visible matter. If gravity is modified, this doesn't make sense. If there is dark matter, a particle that doesn't interact electromagnetically and therefore doesn't get slowed down by the collision, just passes right through the other cluster like a ghost. It makes perfect sense. The bullet cluster is not proof of dark matter in the way a laboratory detection would be, but it is a genuinely strong piece of evidence. And it has pushed most of the scientific community toward dark matter and away from modified gravity, at least for now. I said at least for now, deliberately. I'll come back to that. Let's talk about what dark matter has to be based on what we know. This is the part of the problem I find most beautiful, not because we have the answer, but because the constraints are so precise and so elegantly derived. We know dark matter is not made of ordinary atoms, protons, neutrons, the stuff of you and me and stars, because Big Bang nucleosynthesis tells us exactly how much of that stuff was created in the first few minutes after the Big Bang, and it's not enough to account for the dark matter. We know dark matter is cold, meaning the particles were moving slowly relative to the speed of light when the universe was young, because hot dark matter would have washed out the small scale structure we see in the distribution of galaxies. Cold dark matter clumps, forms, halos, seeds the formation of galaxies. Hot dark matter doesn't. The universe we observe is a cold dark matter universe. We know dark matter doesn't interact significantly with light. It's electrically neutral. It doesn't emit, absorb, or scatter photons at any wavelength. We know it must interact gravitationally, obviously, because gravity is how we detect it. And it possibly interacts through the weak nuclear force, which has made one particular class of candidates enormously appealing. Weakly interacting massive particles, WIMPs. This is a name that physicists gave themselves some credit for inventing, because it is exactly the kind of geeky, self-aware acronym that makes theorists feel clever. But the appeal of WIMPs is not about the name. It's about something called the WIMP miracle. If you take a particle with a mass in the range of 10 to a few thousand times the mass of a proton, and you give it an interaction strength comparable to the weak nuclear force, and you run the thermodynamics of the early universe forward, you get, without tuning, without fudging, without adjusting parameters, a relic abundance of this particle that is exactly, almost eerily, the observed dark matter density. The universe, cooling from the Big Bang, would naturally produce roughly the right number of WIMPs to account for everything we see. This is not a coincidence that physicists are willing to dismiss lightly. The WIMP miracle was, for a long time, the central organizing principle of dark matter theory. It is why so much experimental effort has gone into searching for WIMPs. And here is where I have to be honest with you in a way that is uncomfortable, because I've been in science long enough to know that intellectual honesty is the only currency that doesn't inflate. We have been searching for WIMPs for decades. We have built detectors of extraordinary sensitivity, tanks of liquid xenon buried miles underground to shield them from cosmic rays, crystals cooled to nearly absolute zero to detect the faint recoil of a particle interaction, enormous neutrino detectors repurposed to look for WIMP signals. We have searched, we have not found them. The Lux detector, XENON100, XENON1T, Panda X, each one more sensitive than the last, each one returning the same answer, nothing. Not a hint of a signal above background. The WIMP parameter space, the range of masses and interaction strengths where WIMPs should be detectable, has been carved up and searched and come up empty. WIMPs are not ruled out, but they are in trouble. The simple, elegant, theoretically beautiful WIMP miracle is running up against an uncomfortable reality, which is that the universe does not particularly care whether our theoretical constructions are beautiful. Now, here is where it gets genuinely strange, and I mean that without any rhetorical inflation. The alternative candidates are in some ways even more interesting than WIMPs, precisely because they arrive from completely different directions in theoretical physics and still converge on the same observational requirements. Take axions. The axion was proposed not to explain dark matter, but to solve a completely separate problem, the strong CP problem in quantum chromodynamics, which is the puzzle of why the strong nuclear force doesn't violate a certain symmetry that theory says it ought to violate. The axion fixes that problem. It also almost as an afterthought, turns out to be an excellent dark matter candidate, extremely light, extremely weakly interacting, produced in enormous numbers in the early universe. The fact that a particle invented to solve a problem in nuclear physics turns out to potentially explain the largest mystery in cosmology is exactly the kind of cross-domain convergence that makes physicists feel like they might be onto something real. There are experiments looking for axions, ADMX is one of them, using microwave cavities and strong magnetic fields, but we haven't found them either. Then there are sterile neutrinos, which are neutrinos hypothetical, even more socially isolated cousins, interacting with ordinary matter only through gravity and perhaps through mixing with regular neutrinos. There are primordial black holes, formed before any stars existed, which have had an interesting revival as candidates. There are models with entire dark sectors, not a single dark matter particle, but a dark periodic table, dark forces, dark chemistry, which makes me feel simultaneously that we are being too clever and that the universe is probably much stranger than our cleverness can reach. I want to stop here and tell you something about how I came to care about this problem. I grew up staring at the night sky from New York, which, as anyone who's tried it will tell you, is an act of optimism more than astronomy. The city lights obscure almost everything, but even through the haze, you could see the Milky Way on good nights, not clearly, but as a presence, a smudge of light across the sky that I understood, even as a child, was not a smudge at all, but hundreds of billions of suns, each one potentially surrounded by worlds. The sheer scale of it was almost unbearable. I couldn't stop thinking about it. I read everything I could find. I dragged my parents to the Hayden Planetarium. I wrote letters to scientists, actual letters, because that's what you did, and some of them wrote back, which I found astonishing then and still find touching now. What drew me to astronomy was the idea that you could know things about objects so distant that the light reaching your eye had been traveling since before the Earth existed. That you could decode the universe using nothing but the electromagnetic radiation falling on your instruments. Spectroscopy, photometry, kinematics, these are the tools of the astronomer, and they seemed magical to me, a way of extending human perception across distances that made the mind buckle. But dark matter is the problem that spectroscopy and photometry cannot solve. Not because our instruments aren't good enough, because dark matter doesn't produce light. It doesn't absorb light. The entire toolkit that astronomers built over centuries, everything we know how to do with electromagnetic radiation, is irrelevant to the thing that makes up most of the mass in the universe. This is not a minor technical challenge. It is a fundamental confrontation with the limits of human perception. For all of recorded history, we have studied the universe by collecting light. Stars, nebulae, galaxies' light, radio waves, X-rays, infrared, still electromagnetic radiation, still ultimately photons, still light in the broad sense. And now we are being forced to accept that the dominant form of matter in the universe is, by its very nature, invisible to every instrument we've ever built that works by detecting electromagnetic radiation. We have to find it by other means, by the shadow it casts, by the curvature it induces in space-time, by the paths it forces ordinary matter to take. This is, if you will permit me a moment of philosophical indulgence, a genuinely profound epistemological challenge. Human beings are visual creatures. We evolved to detect light. Our science, for most of its history, has been science of the visible. The microscope lets you see small things. The telescope lets you see distant things. The radio telescope lets you see things that emit radiation our eyes can't detect, but there is no dark matter telescope. There is no instrument that collects dark matter the way a lens collects light, because dark matter doesn't interact with the materials we could build such an instrument from. We are trying to understand the dominant component of the universe with tools that are fundamentally and perhaps irreversibly blind to it, and I think that fact deserves more than a moment's pause. Let me give you a thought experiment that I think captures the situation. Imagine you are a physicist living in a universe where ordinary matter doesn't exist, only dark matter. Everything in your universe is made of these particles that interact only gravitationally. There is no electromagnetism. There is no light. You have never seen anything because sight requires light, which requires electromagnetism, but you are nonetheless a physicist because you can feel gravity, you can feel acceleration. You can build accelerometers, seismometers, instruments that detect mechanical forces, and from these, you construct a complete physics of your universe, gravitational dynamics, general relativity, cosmology. Your physics is correct. It accurately describes everything in your universe. Now imagine that 5% of your universe, a tiny minority, is actually made of something weird and exotic that does interact electromagnetically, that emits and absorbs light, that has all these strange properties your physics doesn't include. And this exotic minority matter is gravitationally unimportant. It barely contributes to the mass budget of your universe. Would you know it was there? You might infer it was there if you looked carefully enough at small-scale gravitational anomalies, at the way this exotic matter occasionally concentrates and produces detectable gravitational signatures. But for most of your history as a civilization, you probably wouldn't notice it at all. It would be a rounding error, an anomaly, something to explain away. That is precisely our situation, reversed. We are the physicists who built our entire science around the 5%. The dark matter is the 95% sitting there, gravitationally dominant, totally invisible to the instruments we built to study the universe. We didn't notice it for most of our scientific history because we weren't looking for it in the right way. Zwicky noticed it in 1933 and was mostly ignored. Rubin proved it definitively in the 1970s. We are still trying to figure out what it is 50 years later. Now here is where it gets strange again, and this time I mean cosmologically strange. The story of dark matter is inseparable from the story of the large-scale structure of the universe, the way galaxies and galaxy clusters and superclusters are distributed across cosmic scales. When you look at the universe at the largest scales, matter is not distributed uniformly. It's arranged in a vast cosmic web sheets and filaments of galaxies, enclosing enormous voids, like the foam of a soap bubble, but on scales of hundreds of millions of light years. This structure did not appear by accident. It grew from tiny fluctuations in the density of the early universe, tiny wrinkles in the distribution of matter that were amplified over billions of years by gravity into the structure we see today. And the story of how that structure formed is, in a crucial way, a story about dark matter. In the early universe, ordinary matter, protons, electrons, was coupled to radiation. The photons and the plasma were locked together, and radiation pressure prevented ordinary matter from clumping. It was turbulent, hot, and resistant to gravitational collapse. Dark matter, having no electromagnetic interactions, was not coupled to radiation. It could clump freely. Even in the early, hot, dense universe, it began to form gravitational potential wells, dimples in the gravitational field that ordinary matter could eventually fall into once the universe had cooled enough for protons and electrons to combine into neutral hydrogen. And the coupling to radiation ended. That moment recombination, roughly 380,000 years after the Big Bang, is when ordinary matter was freed from radiation pressure and could follow the gravitational scaffolding that dark matter had been building for hundreds of thousands of years. Without dark matter, the universe would look very different. The gravitational wells wouldn't exist. Ordinary matter would have had to clump from scratch, relying only on its own gravity, in a universe where radiation pressure had just released it. The timescales don't work. The universe wouldn't have formed galaxies as quickly as it did. In fact, the universe would be much more uniform, more boring, in the way that sterility is boring. Dark matter is not just a puzzle. It is the reason galaxies exist. It is the reason you exist. The gravitational scaffolding built by dark matter in the first moments of the universe is the scaffolding on which every galaxy was assembled, including the Milky Way, including the solar system, including the planet that you and I and everyone who has ever lived has called home. I find this deeply humbling and not in a comfortable way. The thing that made your existence possible is something we cannot identify. The most important ingredient in the recipe for the universe as we know it is the one ingredient we have never put in a jar and looked at. We know it was there. We can see its effects everywhere we look, in the rotation curves of galaxies, in the temperature fluctuations of the cosmic microwave background, in the large-scale structure of the universe, in the behavior of galaxy clusters. The evidence is overwhelming and consistent across dozens of completely independent lines of observation. Whatever dark matter is, it is real. But what it is, we genuinely do not know. I want to take a moment to talk about the cosmic microwave background, because I think it is one of the most extraordinary objects in all of science, and its testimony about dark matter is particularly clear. The CMB is the oldest light in the universe. Electromagnetic radiation that was emitted when the universe first became transparent, 380,000 years after the Big Bang, when protons and electrons combined into neutral hydrogen, and the universe went from being an opaque plasma to being transparent gas. That light has been traveling ever since. It has been stretched by the expansion of the universe from visible light to microwave radiation. When we map its temperature across the sky, it is almost perfectly uniform, the same temperature in every direction to 1 part in 100,000. Almost uniform. Not perfectly uniform, and the tiny fluctuations in temperature, the anisotropies, are a map of the density fluctuations in the early universe. Those fluctuations have a specific pattern, a spectrum of hot and cold spots at different angular scales that encodes an extraordinary amount of physics. The position and relative heights of the peaks in this power spectrum tell us, among other things, the total amount of matter in the universe, the amount of ordinary matter, the amount of dark matter, the geometry of space-time, and the expansion history of the universe. All of this from a map of temperature fluctuations of 30 millionths of a degree. And what the CMB tells us, unambiguously, is that dark matter, something that does not interact with photons, must have been there, clumping while the ordinary matter was locked to the radiation field. If there were no dark matter, the pattern of fluctuations in the CMB would look different in specific calculable ways. The observed pattern is fully consistent with dark matter and inconsistent with models that lack it. This is not a marginal result. This is precision cosmology. The Planck satellite, one of the greatest scientific instruments ever built, has measured this power spectrum with extraordinary precision and returned precise values. Dark matter makes up roughly 27% of the total energy density of the universe, ordinary matter about 5%, and dark energy, which is a completely different and equally baffling mystery, about 68%. These are not rough estimates. These are the best constrained numbers in all of cosmology, and they tell us that we understand directly from first principles roughly 5% of what the universe is made of. I have a friend, I won't embarrass him by naming him, who, when I put it this way, once said to me, "Carl, maybe we should be celebrating. We understand 5% of the universe. That's not nothing." And I looked at him for a moment and I said, "A doctor who correctly identifies 5% of a patient's symptoms and has no idea what's causing the other 95% is not a good doctor. We have a 5% theory of matter. It's a magnificent 5% theory. It's some of the most precise science ever done, but it's 5%. Let me tell you about one more thing, because I've been talking about dark matter and I want to make sure I've shown you how deep the rabbit hole goes. There are theoretical frameworks, not fringe ideas, but serious theoretical physics that suggest dark matter might not be a single particle species, but an entire sector of physics, as rich and complex as the sector of physics we call the Standard Model. In our Standard Model, we have quarks, leptons, gauge bosons, the Higgs field, a whole zoo of particles interacting through multiple forces. There is no obvious reason why the dark sector should be simpler than this. Dark matter might interact with itself through dark forces. There might be dark electromagnetic radiation, dark atoms, dark chemistry. The dark sector might be a whole parallel physics, as complicated as ours, interacting with our sector only through gravity and possibly through some portal particles. This sounds like science fiction. It is serious theoretical physics, constrained by observations, testable in principle even if extraordinarily difficult in practice. The universe might be two physics in one, and we are on one side of the mirror trying to understand a reflection we can't quite see. I want to tell you about a moment in my own intellectual life with this problem that has stayed with me. I was at a conference in the early 1980s. I won't tell you which one. The cocktails were terrible and the arguments were better, and there was a session on the large scale structure of the universe. And a theorist presented calculations showing how different dark matter scenarios produced different large scale structures. Hot dark matter, cold dark matter, warm dark matter, each one produced a characteristic pattern in the distribution of galaxies. And as I sat there looking at the simulations, I had a moment of something I can only describe as vertigo. Not intellectual confusion, vertigo. The feeling that the ground had shifted under my feet. Because I realized, sitting there, that the structure I could see in the night sky, the cosmic web that I had been marveling at since childhood, was not primarily the result of the matter I was made of, or the matter the stars were made of, or the matter any living thing in the universe has ever been made of. It was the result of something else, something we couldn't see, something we didn't understand. The visible universe was like the paint on a canvas, and the canvas itself, the structure, the web, the scaffolding, was dark matter. I had spent my career studying the paint. I hadn't really looked at the canvas. It was humbling in a way that I wasn't entirely prepared for, and I think it's important to be honest when that happens. Here is what keeps me up at night, and I mean this literally. This is not rhetorical flourish. This is a thing that I think about at 3 in the morning. We have no direct detection, none. Every experiment built to catch a dark matter particle interacting with ordinary matter has come up empty. The WIMP parameter space is shrinking. The simple, elegant WIMP miracle is being tested and not finding confirmation. And I am old enough to remember when people were equally confident about other beautiful theoretical predictions that eventually ran into the wall of experimental reality. Beauty is not a reliable guide to truth. History is full of beautiful theories that turned out to be wrong, and I have no particular reason to think this generation of theorists is exempt from that possibility. So I am left with two equally uncomfortable possibilities. Either dark matter is real and is a particle something in the WIMP range or the axion range or somewhere we haven't thought of yet and we simply have not built a sensitive enough detector to find it, or the evidence, which looks so compelling from so many different directions, is pointing us toward something even stranger, a modification of gravity that works in ways we don't yet understand, or a dark sector that interacts with our detectors through channels we haven't opened yet, or something genuinely outside our current theoretical framework. I cannot tell you which of these is true. I cannot tell you what dark matter is. What I can tell you is that it is the largest outstanding question in our understanding of what the universe is made of, and that it is genuinely, productively, gloriously unsolved. And I want to say one more thing about that because I think it matters. Some people hear "we don't know" and feel disappointed. They wanted an answer. They came here for an answer. I understand that feeling. I've spent a career trying to give people answers, and I've learned that the best way to respect your audience's intelligence is to not pretend to answers you don't have. But I want to offer you a different relationship with "we don't know," because I think the right relationship with that phrase is not disappointment, but something more like excitement. Precisely because we don't know, precisely because the question is open. Every time in history that we discovered something that made up most of the universe, when we realized the sun was not the center of everything, when we realized our galaxy was one of hundreds of billions, when we understood that ordinary atomic matter was a relic of a primordial nuclear furnace that burned for the first 3 minutes of time, every time, the discovery changed us, changed what we thought about ourselves, changed what we thought about our place in the cosmos, changed the way we saw the night sky. Dark matter, when we understand it, will be one of those moments, perhaps the largest of those moments, because we are not talking about a correction at the margins. We are talking about discovering what the universe is primarily made of. Whatever dark matter is, understanding it will be a revolution in physics comparable to the discovery of the electron or the structure of DNA or the curvature of space-time. It will be one of the great turning points in human knowledge, and somebody in this room might be part of that. Somebody listening to this might be the person who finds the signal in the noise or proposes the theoretical framework that finally makes sense of all the data, or builds the instrument that catches a dark matter particle for the first time in human history. I am not saying that sentimentally. I am saying it because it is statistically true. The discovery of dark matter will be made by people who are alive today, very possibly by people in this room. And that possibility should not just excite you, it should fill you with a sense of obligation, because this is one of the most important questions in all of science, and it has been waiting for an answer for almost a century, and it is still waiting. 95% of the universe is missing from our equations, missing from our particle physics, our atomic physics, our chemistry, our biology, every science we have built. 95%. And you are sitting here in this moment at the hinge point of history with the instruments and the mathematics and the theoretical frameworks to find it. Not easy, not guaranteed, but possible. Maybe inevitable if we keep looking, keep building, keep refusing to accept that ignorance is the permanent condition. I'll end with this. We are made of the 5%. Every atom in your body, every photon from every star you've ever seen, every piece of information you have ever gathered about the cosmos, all of it is 5% of the story. The other 95% is out there right now, surrounding you, threading through this room, passing through your body at this instant, at roughly the density of 100,000 particles per cubic centimeter, silent, invisible, impervious to every electromagnetic instrument we've built. It is here. We are swimming in it, and we cannot see it, cannot touch it, cannot name it. That should not make you feel small. That should not make you feel like science has failed. It should make you feel exactly the way I feel about it, which is that the universe is far larger, far stranger, and far more generous in its mysteries than we had any right to expect. We thought we understood the composition of the cosmos. We were wrong, and being wrong in this particular way is one of the most important things that has ever happened to science. Because now we know the question, we have the instruments, we have the will. The universe has been keeping this secret for 13.8 billion years. It is waiting to see whether we are clever enough and patient enough and humble enough to find it. I would hate to disappoint it.